everyone. Welcome to GAM303. I see a few familiar faces in the audience, quite a few new ones. Thank you. Really appreciate it that you guys made the last session before the big reInvent party. I hope to see all of you there. In my experience, I tend to usually get the best feedback after a few drinks. My name is Dhruv Tukral. I'm a gaming solutions architect. Actually, also, I'm in Nate's team. And today, we'll be talking about beyond game servers, load testing, rendering, and cloud gaming. I'll be talking for the first 20 minutes or so on load testing, and then my talk is followed by Yuval's talk, and he's the VP of Research and Development at Playcast, and he will be talking about their platform that runs on AWS. So let's get started. So what are the traditional challenges that you face when you do load testing? One is the availability of instances. You want to have the flexibility to be able to launch as many machines, to be able to generate as much load as possible. If the infrastructure limits the amount of machines that can be brought up, and then it limits the amount of load that can be generated, it does not give you a truly accurate picture because you tend up extrapolating those results. A lot of the times I've seen with many customers, their load test environments are actually run in black box or quarantine environments. And this is because of a valid reason. IT is worried about the fact that the load test might be generating tons of requests and packets that might have ended saturating the corporate network. If these networks have intrusion detection systems or intrusion prevention systems, then the load tests might end up triggering those as well. So a lot of the times, these load tests are actually run within a quarantined environment. And then, what happens if there's multiple studios trying to launch a game during the critical holiday season? The load test environment becomes a shared resource and becomes a shared critical resource that there's a lot of contention to actually access. And then come January, your game's launched, everything's stable, people come back from the holidays, everything's stabilized. That same load test environment is not used a whole lot. And so you have a resource that is either used quite a bit in a short period of time or is not used during certain parts of the year. And then geographical load testing. How do you achieve truly geographical load testing? In my past, what I would do is I would end up spoofing HTTP referrer headers or spoofing IP addresses just to simulate the number of clients that were accessing the system. But what this does not tell you, it does not give you a truly accurate picture of latency. And if your application has any dependencies on third-party services, you want to know how those third-party services actually behave from a truly global traffic footprint. And then for all of the above reasons, the load test becomes complex. If the load test environment is running in a quarantined environment with with restrictions on outbound traffic, and if your application actually needs access to those outbound services, what I would do is, I would end up creating stubs, and those stubs would return static data or dummy data. And I've already compromised the quality of my load test. If the load test database is not in sync with the production database, and if there's a mismatch in the size of the data set, as well as if you're making constant schema changes on your production that are not reflected in your load test database, then you're not having an apples-to-apples comparison. So how does AWS make load testing better? Obviously, you have the choice. You have a lot of instances available to you. And you have the choice of launching a few big, beefy instances. So perhaps you can launch a few C3 instances that have a lot of threads running on them. Or you can launch hundreds or thousands of T2 instances and then kind of have a swarming effect for your load test. Load testing on AWS is also cost effective. You can use CloudFormation to generate a load testing stack, bring up your load test environment, and then once you're done with the load test, you tear down that stack and you just lather, rinse, repeat. And for the above reason, resource sharing becomes really easy. In fact, resource sharing doesn't really need to happen because load testing is still cheap. Each and every studio can have their own CloudFormation template, and they can launch their own load testing stack in parallel to the other studios. And there's no stepping on each other's toes when everyone's doing a load test. And so the same process can be applied to multiple studios, and each studio can have a customized version of their load test stack available to them. And with AWS, you can actually achieve truly geographical load. You have 11 regions. We just announced Frankfurt. You can use those same CloudFormation templates to launch those stacks in as many regions as you choose, and then you can start your load test. This allows you to have reduced complexity because since there's no restrictions on limiting outbound traffic, your load test deployment actually behaves like your production deployment, and there's no stubs or anything. I mean, your load test application is the exact same build as the production application with perhaps a few configuration changes on maybe a load test database. Data integrity, so you can leverage snapshots, and your CloudFormation template, when it launches, can refer to the last production snapshot that you took. If you're using RDS, snapshots are taken on a daily or pre-configured basis. Or if you have an EBS-backed volume for your EC2 database, you can use those snapshots, and then you have a parity between your load test database and your production database. And then finally, there's minimal impact on corporate infrastructure. You can use AWS to run your load test as a DMZ. It really does not step on the corporate infrastructure. If you have any services, critical services that are within your own data center, you can still run those load tests, by launching in a VPC, and then still being able to access those internal services. And so, what are the typical steps when you are actually load testing? You want to start out by testing the individual decoupled components, perhaps monolithic components where all the operations are self-contained. Perhaps your databases, your data access objects, your getters, setters. Once you've tested those, then you can start moving on to testing any dependent internal services. A lot of times, every time I work with game companies, billing is a critical internal service that a lot of games need to access. Digital rights management modules are a critical service that everyone needs to access. Perhaps there's an invoicing module, so you want to be able to load test those as well. And then you want to start testing the dependent external services. Perhaps your game uses social APIs. Perhaps you're using Facebook, Google, or Twitter. You want to be able to test those as well. If you're using something like push notifications, want to make sure that you're testing push notifications as well. And then finally, you test the entire stack. You've tested the individual components together, but now you want to know how all those components actually interact with each other in a true end-to-end test. Clicker, help. All right. So let's start with testing those individual decoupled components, those internal services. In this scenario, what if those internal services or components are actually already running on AWS? In this case, load testing actually becomes pretty easy. What you see is a very standard architecture wherein your internal services are within a VPC and your database is in a private subnet, your web servers or your application servers are in a public subnet. And your load testing stack, you just launch your load testing stack in a separate subnet within that same VPC. And why this is simple is because by default, subnet-to-subnet traffic is allowed. So your load test stack can actually access not only your database in a private subnet, but it can also access your resources in the public subnet. And so in this case, I'm showcasing a Grindr CloudFormation template, and I have the link to this template. But this could be a load testing stack of your choice. You could be using Gatling, you could be using Sung, it could be anything. So you have a Grindr console, and you have your Grindr agents in an auto-scaling group. And then your metrics collection and graphing could be something as simple as CloudWatch. And so, let's start testing your master database. If your master database is a relational database, something like MySQL, you can use Grindr for issuing JDBC queries, but you can also use something like JMeter to hammer your database with JDBC queries and then get the response times back and see how it performs. If you're using MongoDB, a lot of game companies use MongoDB, then you have the choice of using two tools, MongoPerf and Mongo-perf. Sound the same, but do pretty separate things. MongoPerf actually tests the disk I/O of the server that Mongo is running on, and it does so by just sending randomly timed I/O operations and then measuring the response times. Mongo-perf is actually a synthetic benchmarking tool that tests the database itself. And so it performs inserts, reads, and updates, and then returns that results back to you. So when you combine the two, you end up getting a test of not only the database itself, but the hardware that it runs on. If you're using something like DynamoDB, because it's a provision throughput model, all you end up doing is you set up your read-write throughput, and you're ready to go. What we do recommend is you use the import-export feature and copy the data into a specialized set of tables that is meant just for load testing. And then when you start load testing, please do involve the data specialist solution architects so they can look at how your tables are performing when you're running the load test, and they can give you guidance on how to optimize the schema, make sure that your hash key is optimal and is being spread appropriately. Oh, sorry. So then you've tested your database, and now you want to test the internal servers that actually access that database. So this is pretty simple. You start hitting your data access objects, your getter setter methods. This is a really good place to test if you're using an object relational mapper. I used to use Hibernate. If you want to be able to see what's the performance overhead of an object relational mapper, you already have the raw results from your database load test, and now you want to see how those components that interact with the database, if there's any kind of delta. So this is a really good place to test that. In this scenario, what if your internal services are in your existing data center? So depending on how these services are going to be accessed in production, if these services are going to be accessed in production over the internet, then make sure your load test stack is load testing these services across the internet. Or if they're being accessed over Direct Connect, then you have to kind of match that in your load test environment. A lot of times, these internal services are accessed over a VPN connection because these are secure services. And so this is a really good place to actually load test your VPN connection's ability to handle production load. If you're concerned about the amount of round trips that are happening between your application and your internal services over a VPN connection, perhaps you can cache some of the data that does not change that often closer to your application so you don't have to make those round trips over and over again. And so testing external services, this part is usually easier to test. What you should just do is contact your account manager, inform them of your intention to load test their API. It's a very simple step, but it's a very important step. What happens if you don't do this? Chances are this third-party service will blacklist your IP, and then because they're thinking they're under a denial of service attack. And so you don't want to get it to that point. So it's a very simple step, but it's also very important. Give them a call, make sure they're aware. They might actually give you a separate set of endpoints when you're doing your load test, so you might have to make that configuration change. And then when you're ready, assuming most likely you're accessing these external APIs across the internet, you launch your stack in one region, another region, and you hit go, and then it's hammer time. So if you want to see me dance to this, you'll have to buy me drinks at the party. I have to let this play out for some reason, but it's worth it. So now you've tested the individual components, you've tested the external components, you want to test the entire stack. At this point, you start simulating entire gameplay sessions, start simulating transactional workflows, get an idea of how component-to-component interaction works. And this is a really good place to identify any bottlenecks within your entire system. If you use profiling tools, this is a really good time to use profiling tools. I would use JConsole or JProfiler. I come from a Java background. Look at your threads, look where if there's any contention. Just kind of make sure that if there's any culprits from your previous load test, you know where to find issues, and just kind of like get a full holistic view of your load test. Let's see. And so what does this end up looking like? This is just a consolidated view of what I've just talked about. So you have your internal services in your corporate data center. You have your external APIs that you're accessing over the internet. Your load test deployment, that is the target of your load test, is within a VPC. And then your load testers are in multiple regions, and then actually hitting your load test deployment. So on a day-to-day basis, what does this process look like? You've seen the overall process from a high level, but from a developer's point of view, how does this look like on a day-to-day basis? You might have load test scripts in a code repository. If you're writing scripts, you check them in, or if there's already an existing list of scripts, then you check those scripts out. And then your developers run a small load test against the load test deployment, and this is to verify the functionality of the scripts, make sure everything is working as it's supposed to, and then when everything is good to go, you check those scripts back and then upload those finished scenarios onto S3. At the same time, on the right-hand side, your load test stack is being launched via CloudFormation. Use your favorite configuration management server of choice, Chef, Puppet, really depends on what kind of shop you have. Push that configuration for, again, depends on if you're using Gatling, if you're using Grindr, if you're using Sung, just push that configuration. In this case, Grindr, will pick up the scenarios from S3, and then you actually start running a full-scale load test. And then at the same time, you're sending data to something like EMR plus Redshift to get graphical analyses of how your load tests are doing. You can use Graphite or Splunk or whatever your favorite graphing tool is. And then upload those raw results onto S3 because you want to have historical data when comparing future load tests. You can apply a similar scenario to soak testing. Does everyone know the difference between a soak test and a load test? Who doesn't know the difference? OK, I'll just go over it quickly. So a load test is meant to break your system, and it runs in a more or less in a very short period of time. A soak test is actually intended to test the system's functionality over an extended period of time. So you could be running it for days, really a predefined period, because it's a really good point to identify any memory leaks, any issues that you might get over long-running processes. And so let's say you're using the similar architecture for running a soak test. This time we're going to leverage the new feature that we launched with S3 notifications. Let's say your developer pushes a new script for the soak test. S3 can actually send a notification to your load test stack. Your load test stack then has two choices. It can either automatically download the update scenarios and restart the test, or it can notify your load test or soak testing team and basically tell them that there's a new scenario. Do you want to run an updated scenario? And so, here's some final thoughts on what we just talked about. You want to automate everything. Use CloudFormation. It gives you the ability to launch stacks very easily across multiple regions. Use your favorite configuration management tool. Make sure that you're combining the two to make your life really, really easy. Record everything. Data is key. Storage is so cheap nowadays. There's no reason not to keep historical data. I've heard quite a bit when people say it's better to, more often than not, it's better to run a simple analysis on a large data set than a very complicated analysis on a small data set. And then save money. Use CloudFormation. Only use your load testing stack when you need to. Tear it down when you're not using it. Leverage spot instances. If you've automated everything, make sure that you're running your load tests in the odd hours of the night, so you can get guaranteed spot instances. This will make sure that your load testing environment is actually pretty cost effective. If you're using ELBs as a front for your application, connect with the ELB team or your technical account manager or account manager and make sure that they're aware that you're going to be doing a load test so they can pre-warm those ELBs. This is a link to the CloudFormation template for the Grindr load testing stack. This is not an official template, but it's really, really well documented. And it's a really good place to get started if you just want to try something really quickly. Really, really well documented. And then the final and the most important step is you still have to hope and pray at launch, because all of these tools are just meant to prepare you for what is to come. It's meant to prepare you to identify any issues. In the end, experience is the best teacher, and the more and more you do this, the more you'll get better at it. But these tools are available to you. Make sure you use them, and have fun, as much fun as one can have doing a load test. Thank you, everyone. And now, Yuval from Playcast.
Thank you. Okay, so thanks for coming. I want to talk with you today about cloud gaming, and how Playcast actually moved from a private cloud, from on-premise cloud, to the AWS and leveraged the ability of AWS to be elastic. Let's start with what Playcast is doing. So Playcast is a cloud gaming company. We take a game and we run it on the server. We don't run the game on the client, we run it on the server. The game is run and rendered on the server, and then we stream it as video in real time. The frames are being sent as encoded video to an end device. It can be a TV, a set-top box, whatever device you like. And the gamepad is connected to that device. So the gamepad command will be sent back to the server, and by that, we basically bring a console-like experience to any device, TV, set-top box, etc. Not only we run one game on the server, we actually run multiple games. So we have the ability to run multiple games in parallel on the server. We are running many servers, and we have a complete management system. So the management system enables us to decide which game to run on which server, whether the system is loaded, etc., to collect data, what people are playing, when are they playing, and make decisions according to that. So we don't develop games. We actually provide a platform that with that we can deploy games using cloud gaming. So we have agreement with many publishers. We actually have today over 100 titles on our platform. You can see the list of the publishers. We have more publishers. Actually, it's very interesting. Today, we released a game from Konami, which is PES 15, both on Street Date. It is also on our service. So today, a game that was sold to the public is also on our service. So it's very nice. So today, we operate in 3 countries, France, Portugal, and Korea. The way the service is working there is by having servers on-premise, bare metal servers on-premise in those operators' data centers. So basically, when a customer has a set-top box at home and he switches to a certain channel on the TV, he can get a cloud gaming service powered by us. Several months ago, we decided we want to go over the top. So we took the Ouya box and launched a trial service over the top. When we wanted to do that, we actually thought, how are we going to do that? Because we're going to need to deploy many servers and have a large investment in CapEx for those servers. So we wanted to look on how to do that in a more efficient way in terms of the cost. So this is when we looked into AWS. And we actually launched this service using AWS, and it is a live service today, operating in North America and Europe. So let me show you how this service looks like. I'm going to show you now a real-time demo. Thank you, Drew. What you see here, this is the fun part when I need to talk and play together, so I hope I make it. What you see here is basically a game which is running on AWS in San Francisco. We stream it in real time playing. This is me, right? See, I'm stopping, it stops, right? So I'm playing, and this is a game being streamed in HD, 720p, in real time from San Francisco. And I'm playing that on the system. So all I have here is a gamepad connected to a very small device, an Ouya device that doesn't have any processing capability to play this, to run this game. This is a AAA game, and you can see that I can actually enjoy a AAA game on such a device. And again, this is from San Francisco on a G2 instance running in real time. So because this is cloud gaming, I can also pause the game. I can exit the game, and then I can have exit the game, yeah. And I can now have a whole catalog being brought to me. Again, everything is streamed from G2, so in a sense, it's another game being running on the service. So now I have a catalog that I can browse the games that are available. This is a UI which was developed by us, and it is a streamed UI. Nothing is running on the box itself. And I will choose a different game. Let's see. So let's take this one. So I launched the Sprinter Cell game. And now the same process is happening. So the system allocates resources for this game. This game is being launched on an instance. There might be other games running on that instance as well. And I'm going to get the stream in real time. And you see how quickly the game loads on the system and how quickly you can start playing the game. Yeah, so we can continue playing like till the end, so let's stop it here. Okay. Yeah. So how does it work? We wanted to move from a private cloud to AWS. And we looked into what kind of an AWS components do we need in order to drive such a service. So the AWS components that we are using in our service are first the G2. So the G2 is the streaming server that on that server we actually run the game, render it, and stream it as video. The G2 has an NVIDIA Grid GPU that we are using, and it is basically the foundation of running the game. The G2 has a 60 gigabyte of SSD. Now, if you take a collection of games, you saw in my demo that we have like tens of games or even hundreds of games. If you try to store them all on 60 gigabyte disk, you'll come into a space problem. So in order to solve that, we actually use EBS. So we attach an EBS to the instance, and we store the games there. When you're doing cloud gaming, you want to give the user the ability to return to the game from the same location he started. So you need to save the progress. And for that, we use S3. And I will explain in a minute why we chose to use S3 for that. So we use S3 to store the game progress. And we take everything and actually bundle that within an AMI. So using an AMI, we can actually instantiate the whole system, the whole instances on the fly. Since we are launching instances and terminate them on the fly, we need to use the API. So we are using the AWS API in order to instantiate instances, to terminate them, and to have the system manage that. So we are using the .NET APIs for that. So how does the architecture look like? So what is the flow? When you take all those components, how do you connect them together in order to have a complete system? So let's look on this flow. So here we have the management system. And there is a game streaming server running with games. And let's assume that at some point in time, there is a lack of space. You cannot run more games on that server. So at that point in time, we actually instantiate a new G2 instance and an EBS. So now we have those components up in the air running. But you cannot still use them. You need to connect them. So basically, using an AMI, we connect them. The AMI not only connects them, but using the AMI, we actually have immediately all the games stored on the EBS. So we don't need to copy everything again and again. It's instantly there. Not only the games are instantly there, but also the software stack of our system is being loaded on the G2. And now the streaming server can be used in order to stream the game. And we can start playing. So this is actually what we saw before when you saw the demo. Actually, this was the process that was happening. And we continue playing. But what happens when I stop playing? So I stop playing, or the game is game over. Now we need to store the data. We need to store the data of the game so that when I will play it next time, I will continue from the exact same location, my progress in the game. So why not just keep it on the EBS? So if you keep it on the EBS, there might be a case where that instance is being terminated because there is no need for the instance at the moment because there is no load on the system. So we terminate the instance. So if we keep the progress on the EBS, we will lose the data. And this is not something we want to do. So we store it on the S3. And once we store it on the S3, basically it's available to all the next session of that user running that game. So I can terminate the instance now, and I still have the data. So when you take such a complex service, a very performance-demanding service, move it from a bare metal infrastructure to the cloud, what are the challenges that you're starting to face? So the first challenge is performance. We are running games. These are AAA games running in the cloud. Can we get the same performance we are getting on a bare metal server from the virtual server? So that's the first challenge. And the second challenge is the throughput. So we are running many games on an instance, I/O operations. Can the EBS give throughput performance as if it was a local disk? So as you can imagine, because you saw it's working, the answer is yes. But let's see how we got into that conclusion. So let's start with the CPU comparison. So what you see here in the graph is actually the CPU usage of Dirt 3. That's the game I actually played before. And you can see the CPU usage both on the G2 instance and on a bare metal server. What you can see, the usage of the CPU is almost identical. There may be slight changes. So in terms of performance, the G2 gives the performance that you need in order to run the game. You don't have any penalty by running the game on a virtual server. So this is great. But what about the GPU? So the G2 has an NVIDIA Grid. The Grid card is the base, is the GPU that we are using on the G2. What you see here in the graph is a histogram. We took actually the Dirt 3 game and we played it. We played it on a bare metal server, on a physical server, and on the G2. And then we measured how much time does it take to render a frame. So when the game sends a frame to the GPU, it takes time to render the frame, and then you get the frame back, and you can encode it and send it this video. So how much time does it take to render a frame? And this is what this graph illustrates. So you can see that the majority of the frames for Dirt 3 are around 4.5 milliseconds. And you can see that it doesn't matter whether this is a G2, which is a virtualized environment, or it's a bare metal server. In both cases, you can achieve the GPU performance that you need from the G2. So running a game on a G2 doesn't imply any performance overhead from the GPU side. The last part of the challenge is the EBS. So GP2, as you know, is the SSD-based EBS that gives a very, very high throughput in terms of PIOPS. And the question is whether that EBS can serve as a disk as if it was a local disk for the server. So what you see here is a graph that illustrates the number of IOPS which are measured on the system, on a G2 instance and the EBS. What you can see that we don't get any overhead, or we don't get into a peak points, even though we are running multiple games on the instance. So what you see here is the PIOPS that the system requires at each point in time. And we don't reach any peaks, and the EBS actually gives us the same performance that we would achieve from a local hard disk. So when you talk about games do a lot of I/O operations, and as you can see, running them in the cloud using an EBS can work. So now we have a system that we can run in the cloud, and this gives a lot of advantage because the cloud is elastic. And when you look on cloud gaming, and this is data from our existing servers in France, Korea, and Portugal, and you can see that actually a cloud gaming service behaves in terms of the consumption, the user's consumption, the same way any other TV servers behaves like. So as you see here, the playtime that people, when people are playing, they're playing during peak hours. So there are peak hours and low hours, and this is exactly where AWS helps us. So once we start to reach to a point of the demand, we can instantiate more instances. Once the demand goes down, we can terminate instances. So AWS basically gave us the possibility to manage that and be much more cost efficient. We don't need to have servers up and running waiting for a demand. We just instantiate them on the fly. And the way we manage that is, again, by using the APIs to instantiate the instance, set the AMI, connect the EBS, etc. What we need to note is that when you launch and when you launch an instance, it can take some time. So it can take up to several minutes. And that needs to be taken into account when you design some kind of a load balancer system. So our system doesn't use the AWS load balancer. We actually created our proprietary load balancer that takes into account what will be the demand and will instantiate the instances accordingly. So what did we see today? So first of all, we saw that you can move from a private cloud to the public cloud, to AWS. And while everybody knows that, it doesn't seem trivial for gaming. Gaming seems to be a unique workload that it is not trivial that you can move it to the cloud. So we showed you that we can do that on the cloud. Working with AWS enables us to deploy global service without the need to invest into expensive hardware. So we can just go there, launch the service, and if there is a demand, we launch more instances, and we scale as we grow. We don't need to invest any hardware investment in that. When we are doing cloud gaming on AWS, you are using not only the G2 as an instance, but you're using many components. So we are using G2 in order to run the game and stream it. We are using EBS because the G2 has only 60 gigabyte of SSD. And using the EBS, we actually get a local disk performance attached to the instance. We are using Amazon S3 that enables us to manage and store the progress of the users in the cloud. And we can get that user progress no matter where the user is playing and no matter from which device. And we use the AMI in order to bundle everything and instantiate the instances on the fly without the need to set it up every time from scratch, copy the data, etc. So the games are instantly being loaded on the EBS, and the software stack is being loaded on the instance. And performance. So performance is critical for cloud gaming. And as you saw, you don't get an overhead, or the overhead is very minimal. You can run games on G2, on AWS, and get the performance as if it was a bare metal server, which is not a trivial thing to do. And last, elasticity. So using AWS, when you run a service which has a peak time pattern usage, okay, and hours where you need more servers and hours when you need less servers, this is where you get the benefit. We get a benefit from AWS. It enables us to be elastic and to scale as we grow according to the hourly demand and be much more cost efficient. So with that, I want to thank you. We want to thank you.
Oh, thanks, everyone.
Thank you very much. This is the link for give us feedback. If anybody wants to play, you're welcome. And thank you.